Okay. So last class, we talked about the sunflower lemma and kind of saw the full proof of the improved bounds, right? And today we are going to switch to a new topic. But before that, let me just briefly summarize what else one could do with the techniques that we had and what are its limitations, and then we'll go on. Okay. So today's and today. And we're going to start a new topic, communication complexity. And maybe we will even talk about it for the next topic too. We'll think about that. And the last one is information complexity. Okay. So that's a new topic. So this one, these notes are on a new notebook, which is linked on the course website. Okay. All right. So okay. And so recall the sunflower conjecture, which was kind of our starting point, was that for every R, there exists a constant CR such that every family of sets F of size less than or equal to K and contains a R sunflower. Right, so there's this conjecture, Erudition-Rado, which said that if you have a set family, if the size of the sets is small and the number of sets is sufficiently big, in particular, it's exponential in K, there's no dependence on the size of the universe, it must contain an R sunflower where R is some constant. Okay. And if you let n of F comma R, sorry, n of R comma K be the smallest number to guarantee a sunflower, then we saw that this is true. There is a family of sets of size R minus 1 to the K sets and does not contain a R sunflower, right? This was this kind of row-based construction. And what we saw over the, kind of the last couple of lectures was this part. Okay. And this is kind of significant improvement over the 60-year-old bound. The previous best was essentially right. So this is where things stood for a long, long time. And then we had this improvement. Okay. Right. So the biggest improvement was in 2020, where this was like log K, log K, and then people shared off everything, the log terms, and we got this. Okay. And you might wonder, okay, so how important is this log K? It turns out it's actually quite important, especially for applications in communication complexity and so on. It's kind of a little bit, the applications are quite intricate. So I won't have time to explain why it is important. It also has connections to fast matrix multiplication algorithms and so on. but sunflowers are so central, they keep showing up everywhere because two reasons. One, it's a very simple structure and it's very helpful in many different contexts. Okay. But along the way, we didn't just show this bound. Yeah. Some of them, yes. So far, at least the constant has not been bad, right? But the dependence on K is what hurts. Okay. It can give, maybe in some applications it might matter, but more or less the belief is, or at least I would be surprised if somehow magically you would get like a tower of R's, but exponential dependence on K, especially given the current techniques. Okay. All right. So, but we didn't just show this, we actually showed something stronger, right? So we didn't just prove this thing, we kind of showed something stronger, which was the spreadness lemma. As I said, the notion of spreadness itself is quite useful. Maybe it'll show up in the last topic of the class too. Okay, so what was the exact thing that we said? We said F is a family of sets of size K and is S spread where, let's say, S is log K. Maybe let me just write it as some log K. Okay. And W is a random subset of U of size Okay, so this is the spreadness lemma that we showed. Okay, spreadness or robust sunflower, kind of equivalent. A small tweak that you can make in the definition, which is what usually called robust sunflower lemma, but let's not worry about that. Okay. So this is slightly stronger or kind of incomparable, at least because you have some probabilistic thing and you're saying that if I pick a random set of certain size, then it contains one of the elements in my family with high probability. Okay. And there's a small, this is more or less equivalent to the following thing as well. So instead of picking a random subset of size exactly, U over R, I can build the set W by including each element independently with probability 1 over R. Yes, it's like saying I'm going to pick out of 100 elements, I'm going to pick a random subset of size exactly 10, or each element is going to be present in my set with probability 1 over 10. Kind of almost equivalent, especially when U is very big, the distributions tend to be same, and the same thing holds. So let me where each I belongs to U is in W with probability 1 over R. Okay, independently with probability 1 over R. Even then, more or less the same statement holds. You might have to change the constant a little bit, but the same thing holds. Okay. And this is a pretty useful version. If you know what DNFs are, this is really connected to the satisfiability of certain DNFs, and that is a very important observation for applications in computer science, for example. Okay. Just as a hint, let's say, F equals, I have sets S1, S2 up to Sn. Then I can define a DNF. Okay, saying pick a element, pick a 0, 1 string X. You can think of X as basically the support vector of W, right? And it's saying phi of X evaluates to 1 if some, if one of the sets is completely set to be true under X, right? So, W subset of U, I can set X equals support of W belongs to 0, 1 through the U. Now, okay. So this is one connection to DNFs, right? And this is quite helpful in proving properties of DNFs. You can show that DNFs can be approximated, simplified a lot just by using this, okay? So if I have a DNF with maybe 1 million terms, but each one only involves 5 variables, then you can show, in fact, I'll ask you to prove, maybe I'll ask you to prove in midterm, that you can use sunflower lemma to say, I can get rid of most of the terms. There is like a core element number of terms that I can focus on and get rid of most of the things. This is called DNF sparsification. You can simplify DNFs tremendously just by using sunflowers. Okay. So on and so forth. There are lots of applications from this connection, for instance. Okay. So this is kind of, one connection. Right? The second connection and this is a setting where the improvement actually makes an even bigger difference. Improvement and the strengthening in terms of spreadness makes an even bigger difference is to random graphs. Okay. And let me ask you a simple question. Suppose I generate a random graph on n vertices by adding each edge with probability p. Okay, each edge independently with probability p, right? So if p is like 0.1, then you're adding a lot of edges, or your p could be pretty small too. Maybe I'm only adding overall only log n edges, but p is like log n over n or something like that. Okay. Now, often, when you have such graphs, what you're interested in is, okay, for what is the minimum value of p so that you're guaranteed that the graph has some nice property. What is the minimum probability p such the graph is connected? What is the minimum probability p that the graph contains like a cycle and so on? Okay. So this has been studied a lot. There's a whole theory behind it. But I can ask you one simple question, what is the least p such that probability g generated in this random way contains a Hamiltonian cycle. Is greater than or equal to half. Okay. At what point would you start seeing a Hamiltonian cycle? Okay. And what's a Hamiltonian cycle? So I can imagine a graph like this. Okay, I'm first drawing the cycle, so it's kind of clear, right? So Hamiltonian cycle is just a cycle which visits every vertex once, right? So for example, this would be a Hamiltonian cycle here, right? In some sense, Hamiltonian cycles seem like a very special property of graphs, right? Not every graph would have it, okay? But this is asking, what if I just generate a graph at random? And if I generate maybe P is very, very high, you're maybe very likely to contain a Hamiltonian cycle. But what's the limit at which you will start seeing this cycle with high probability? Okay, seems like a very complicated question. It is indeed it was indeed a complicated question. There was a pretty, intense proof. I forget the citation, but from like 90s, which proved that basically when P is roughly some constant times log n over n, we start seeing cycles. Okay. And yeah, so, but this was like a theorem. I forgot the citation, but I can look it up for you if you want, but it's quite a non-trivial thing. Now, how does this connect to sunflowers? Well, can you think of some way of phrasing it in the language that we've seen over the last few lectures? I mean, if we can find a connection, that's already kind of something to play, right? Often some big steps can happen when you look at things in different lenses, right? So a priori, this question has a lot of structure in it. You have Hamiltonian cycles, you have graphs. These are very special, but you can abstract some of that out, ignore some structure, and go back to just sets and hope that something nice happens. Okay. In particular, let's think of what this graph is. We're including each edge independently with probability P. Okay. So in some sense, the graph so G has vertex at n, and the edges are n choose 2, right? Pairs of things. Let me call this W now. Now, what can you tell me about this set of edges W? Each edge is present, the way I'm generating the graph, each edge is present independently with probability P, which is kind of the same model that we had, right? So now the question of Hamiltonian cycle reduces to a question which very much looks like this. So what should the corresponding set system be? What would be the nice thing to look at? And I want to say I can capture this question of Hamiltonian cycles just in the same language that we saw by defining a suitable set family. So what should that set family be? Exactly, right? So I can look at the universe as all possible edges. And now I'm looking at subsets of these things, right? So FB S such that S subset of U such that S is a Hamiltonian cycle. Okay, let me call this Hamilton, right? So now this question that we asked is the same as asking for what P can we say right? The exact same question we studied in the context of spreadness lemma, right? Except the family is very special, right? Does it make sense? Okay. And W is exactly the same. Each one is included with independently with probability P. You got rid of almost all the structure, or not got rid of it, but at least all of it went into this set family. Okay. And every set here has size which is n. Okay, like the K there earlier that we had was n. All right. And in fact, there's a very complicated proof there, but you can use this. Use the new spreadness lemma to get like a very quick proof of this theorem about Hamiltonian cycle. You just have to show that this F ham, this is an Eisenhower family to be spread and so on. Okay, so that's another connection. In fact, in the same context, there was this very beautiful conjecture called Kahn-Kalai conjecture. And which was resolved using similar arguments by Jin-Young Park and Hui Pham in 24. Okay. All right. So these are some kind of applications. One directly to DNFs and DNF sparsification, which is useful for algorithms, and the other in probabilistic combinatorics, where you're trying to understand when certain structures arise in graphs. Okay. Earlier, you had to use like complicated properties of Hamiltonian cycles, first moment method, second moment method, all kinds of things. But now you can just apply the spreadness lemma and spreadness. Okay. Any questions about this sort of high-level view or applications? And there's also a stunning connection to matrix multiplication, but that's that's going to take a whole lecture, so I'm not going to talk about that. And lastly, let me say one remark, which is that so that if you compare the true conjecture, it was the CR to the K, but here in the spreadness, we are kind of always losing this log K here, right? That's how we got instead of getting a constant to the K, we got this log K to the K, okay? And it turns out that for spreadness lemma, the log K loss is tight. You cannot get rid of that. So if you want to get the true sunflower conjecture, you have to find some other approach, or at least find a way to tweak it beyond this one. This is a stronger form of the sunflower lemma, and it is indeed stronger in the sense that you cannot improve it quantitatively to match the usual sunflower conjecture. Okay. So just as a remark, the spreadness lemma is basically tight. So we need spreadness to be bigger than R times log K. Okay, so ideally we could have hoped to get the full sunflower conjecture. Maybe I just need to shave off this log K here, and I would get the full proof. of the sunflower conjecture using the spreadness approach, but it turns out that's not possible. Okay, not possible because this is a stronger statement, right? It's a counter. So we have a counterexample to getting rid of the log k for the stronger statement, but not for the original sunflower. All right. Okay. So that's all I wanted to say about the sunflower lemma. And if there are no other questions, we are going to make a huge context switch and start talking about a completely different topic, right? But I encourage you to think about these two applications. If you'd like to know more, I'll point out some references. And as I said, this view, in fact, I have a paper on DNS sparsification, which really exactly uses this. Okay. All right. Okay. So now let's switch gears a little bit, and we're going to talk about communication complexity. And within that, we're going to focus on one specific problem. And as I said from the beginning, we've been using specific important problems as excuses to learn some important ideas and theories, right? Like the undirected ST connectivity was our way or cue to learn spectral graph theory, right? Sensitivity conjecture was our cue to learn like this Cauchy's interlacing theorem and how you can play with eigenvalues. Sunflower lemma was our cue to learn about spreadness, the ideas of like, doing things gradually instead of going in one shot, and encoding. So we will use a specific problem in communication complexity, which is again a very important problem to understand something about information, not just in the usual sense, but also in the context of communication. Okay. All right. So, but first, I need to motivate the basic problem that we're going to start with. All right. So what is communication complexity? You can think of much of computer science as trying to optimize various resources. Most of the time you're optimizing for time, sometimes memory, sometimes randomness, as we were doing in the first portion. For this topic, we are going to try and optimize communication. So our only bottleneck is going to be, our only sort of quantitative thing that we're going to care about is how many bits do we need to communicate to solve certain computational tasks. Okay. So just imagine, I'm Alice, and now I have Bob. So this is Alice, Bob, and Alice has some input X, Bob has some input Y. Okay. And they want to compute some joint function of their inputs, right? What does this mean? There is some function they are interested in, which depends on both their inputs. If it only depends on their thing, they can do it. Alice can do it, or Bob can do it. But it depends on both of their inputs, right? And so that means that they have to communicate because they are separated. And compute the answer f of x comma. Okay. We are going to view Alice and Bob as infinitely powerful. I mean, it's not needed, but the point is that just imagine that the communication is a real bottleneck. And in fact, we've been through stages in practical computer science where this comes and goes. Right? Initially, computing was a bottleneck, but then bandwidth became a bottleneck, and then bandwidth became too easy, and computing was a bottleneck. And I would say now we are back in the stage where the bandwidth is a big problem because you have these huge data centers, and then you have to really manage, if you're doing even GPU programming, even on a single chip, you're really trying to manage the bandwidth of the caches and so on, right? So the bandwidth is a problem. Okay, it doesn't even have to be across different servers. It could be on the same chip, but you have two different processors, and you have to manage how much communication they need to do between themselves. Okay, so we are back in the setting, I would say, by and large, where communication is really an important bottleneck, right? So the question that we're going to ask is, what is the best protocol in terms of number of bits for computing this? This should be the first order bit, and of course, after that, you can try and minimize. Okay, how many rounds of communication do you need to do? How many bits each time? Maybe I can also initiate a trade-off. If I have k bits of communication, t amount of time, how do I play with these two things and kind of get the entire spectrum, right? But first, let's ignore the other things and try to understand just the communication to get a handle on that. And then we'll talk about the other stuff. And then we can build theories for the other stuff, right? So what is the best protocol? Okay. And so we can also have, just as we had in the case of algorithms, we can have deterministic and randomized protocols. So deterministic just means that answer is always correct. Alice and Bob both will end up with the exact f of x comma y, no matter what. Randomized means that, they get the right answer with probability greater than or equal to 9. Okay. We will, at least for this segment, we'll focus on randomized, but it's helpful to understand that there are these differences, kind of to get a sense of the models and what how communication complexity is different or can be different from traditional complexity. Okay. All right. And even in randomized, there are two different versions. One is called public coin randomness, one is private coin randomness, in the following sense. Okay, so I can imagine there being two different versions of randomized where Alice has some random bits and Bob has their own sort of random bits. Okay, so if you imagine, you're writing some program on your thing and you're trying to do something on a server, then do you exchange the seed that you're using here with the server or not? Or somehow the seed is something common sitting in the sky that both of you are using. Okay. So this is called private randomness. And this is called public. Okay, so public meaning both Alice and Bob have access to the same random bits. Private means that each one has access to only one. Okay, so for a function f, I mean the domain we'll make it specific soon. So you have some inputs X and Y, and you have 0, 1. And I can define different notions now. So one is, might not make it too complicated. Okay, so I can talk about the deterministic communication complexity of F, right? So how many bits do Alice and Bob need to exchange in the worst possible inputs to actually compute F, right? So this is minimum number of bits needed to compute F, okay? And I can also have randomized private, and let's say 0.1. So this is just some notation, natural notation, meaning, they only have private randomness here. And 0.1 just means that we want them to be correct with probability 0.9. 0.1 is the error probability, okay? Equals minimum number of bits needed to compute F with probability greater than or equal to 0.9. Okay. And then finally, similarly, I can have our public. Okay. Now, how are these three connected to each other? What do you think is the relation between these two? Is there an ordering between them? Yeah. Yes, deterministic is always more, right? Randomness just means that you have more resources. And private versus public? Well, public, yeah. Private's more, because you can basically simulate private, right? We're not counting how many bits you have. We're just saying somehow the difference between these two is that maybe it's helpful for both of them to use the same seed. If that's the case, they need to exchange the random bits in some sense. We need to synchronize what we're using. Okay. Think of it like, let's say we have people playing, Alice and Bob want to play poker. Right. So if you think of playing poker, it's really helpful to have public randomness because they have to shuffle the cards at random. But then if each one has their own shuffle deck, they have to basically exchange the entire shuffle pattern to kind of make it work. Okay. So that's kind of a different setting, right? Okay. So this is just kind of the basic layout. And let's look at one simple example to kind of get a sense of the problem. Okay, it's not the main thing that we're going to study, but just as a precursor to get some understanding of the definitions involved. Okay, this is, in some sense, the simplest communication problem you can think of, which actually gets solved many, many times or millions of times every day, is equality. Meaning, I want to check if the file I have and the file you have is the same, let's say. And maybe I have a cloud copy. I want to check if the file has changed or not. Maybe I have some other document database. I want to check if it's the same database that you have. Or is there some corruption? Okay. As I said, the domain could be something pretty different, but we're going to simplify it just for clarity of notation more than anything else. Okay. So let's say Alice and Bob both have n-bit strings. Okay. It could even just be a full database, a database of images and so on. Doesn't matter, but just to begin with, let's think of them as bit strings. And we'll say 1 if x equals y and 0 else. Okay. Very simple function, also seems very valuable function to compute in the communication setup. Okay. All right. So now, what is the deterministic complexity of this? We ask, okay, what is dt of EQ? What's the trivial protocol? Send everything. I send my string X, or basically if you have it, I have a database of images, you have a database, I want to check if they're the same, I'll send my database to you, right? Okay. So that's a trivial upper bound, but is this the best protocol we have? Maybe there's something cleverer I can do. Maybe I can do some kind of, if I think of it as an integer, do some kind of crazy binary search or whatever I want. Well, it turns out, yeah. That's a good question. Technically, yes. So, or you can simplify the model and say, we will say its function is computed when at least one of them knows the answer, or otherwise we just add a +1. Okay. So the model is pretty robust, except for these small additions. Okay. So that's why, in fact, I didn't define it fully formally because it's a little bit tedious to define what a protocol is. I had to come up with like a function which looks at the transcript so far, my input, and so on. But we kind of, it makes intuitive sense. Okay. All right. So it's less than or equal to n, meaning Alice sends n across, and then Bob knows the answer. Okay. And it turns out that this is the best you can do. There's no other protocol. In the deterministic setting, if I always want the correct answer, then there's no savings you can have. Okay. And you can prove this by some kind of, nice pigeonhole argument, but we're not going to do that. Okay. Let me not write it as n factorial is equal to n. It's an exclamation mark. Yeah. Okay. All right. Now, how about randomized? As I said, equality is something that we solve many, many times over on a computer. Every time you log on to the internet, in some sense, you're logging onto a machine or any, you're entering your password, right? Someone there has to check the password that you entered matches whatever they have in their database. Okay, passwords are small, but if you have files, then you want to check if the file has changed or not, right? You're not sending the whole file every time to check if it's changed or not. Okay. And that actually shows up in that there is actually a much better protocol for equality. Okay. So for instance, with public coin randomness, I can always solve equality with just 5 bits. Okay, it went from n to 5. All right. And that's very important. As I said, we keep using it every time. All right. And have you used Git before? You see this in action there. Like you'll see this hashes, right? Which is exactly running the protocol that we're going to talk about in a second. Okay. They do something more because they can keep track of some continuous changes. So they make it a little bit more efficient to compute. But that's, as I said, you first figure out the most important thing, most significant bit, and then you can tweak the system or adapt it better. Okay, this is for public coin. And how about private? It turns out that the private thing is log n plus O. Okay, you can't quite get 5, but you can get exponential savings over deterministic, log n plus a constant. Okay, and this log n is necessary. Okay, so there is a log n gap between private and public, but yeah.
100% here, like for like a really
No, this is like 0.1.
Oh, okay.
Right? So the phi depends on the 0.1. If you want to boost the 0.1 to 0.01, then I might have to repeat the protocol, so that'll go change.
Oh.
Okay.
Is 0.1 like cancel?
Yeah.
Oh.
Yeah. So basically, once I get 0.1, I can repeat it like, some number of times, and then it keeps decaying exponentially. So if I get a constant success, most of the time I'm good because I can boost it by repeating, right? And you can also sometimes do even better boosting, but typically getting 0.1 is a very good indicator. And most of the time, once you get 0.1, to get epsilon is like log, let's say delta error is like log 1 over delta. Okay. All right, so this is good. Now, let me say, as I said, I want to give some sense of how communication complexity works. So let's think of this claim. Maybe let's not even go there. Let's try O of log n. So how can I solve equality with only log n bits of communication instead of n bits of communication? Any ideas? Yeah?
I mean, log n seems like you're saying you're giving like a position.
Mm-hmm. Right. But then the issue is, what if my string only differs in 1 bit? You don't know which bit they differ in, right? X and Y, in fact, that's what happens. That you have a huge file or database. I made one change. And the server doesn't know which change. So how do you communicate in some sense? If you have some steady state or something, you can map just the change, which is what happens in systems. But when you're resetting or something, you don't know where the change happened. So how do you get it? Yeah. Checksums are actually very relevant. That's one way. Basically, you can add some redundancy into your X. Okay. The abstract way to do this is I have X and Y, right? I can introduce some checksums are basically some kind of encoding of X. Right. So checksums are basically a way to code information so that you introduce some extra redundancies. Meaning, if X and Y differed in 1 bit, I want these encodings to differ in many, many positions. Right? So it's like an error correcting code, which are what checksums are designed to do. Okay. So one nice abstract way to do it is to say, I can use an error correcting code. And in fact, this is what gets used for specific error correcting codes. When you use checksums, these are specific error correcting code, so you can use that. So meaning, let's say suppose I have a code like this. If X is not equal to Y, then okay. If they are distinct, then the two encodings differ in 90% of the coordinates. Okay, so even a single gap gets amplified into 90%. Okay, it's a way to identify corruptions. Okay, yeah. Right. So the question now becomes, we can go back to the protocol that you suggested, which is, so now, so what's the protocol? Alice computes. Actually, let me write it this way. In fact, because this is what is a practical implemented, pick an index I in M, send the ith coordinate. Okay, but you also have to send I, right? So you send I and the index, right? Pick an index I at random. And Bob, what does Bob do? Check if the bit matches okay. So Alice sends this message to Bob, and Bob checks, okay, I know I now. I'm going to compute the ith bit of my encoding and check if they match. If they match, it's just going to say, okay, they are the same. If they don't match, they are different. Okay. And the probability of success is 0.1 because they agree 90% of the coordinates. So the chance that I pick one of the bad coordinates is only 0.1. Right? But what is the communication complexity? I need to send this index I. If it was public coin randomness, then I is also in the sky, so I don't have to send I. Okay, so that's okay. But typically you do have to send something about the seed that you're using for your hash so that the server can match it. Okay, if there's no synchronization, you can be in trouble. Right? So cost is log m plus 1. Okay. Right. And it turns out that there exist error correcting codes where m is O of n. It's just a constant times n. Okay. So in part, I mean, we don't even need the constant times n, but that means that basically log m is log n plus O. Okay. If you want n squared, which gives you 2 log n, you can build it just by hand. The other one is a little bit tricky, but even that you can. Okay. And if you know checksums, that's basically one way to do this. You won't get exactly O of n, you might get n squared, but in the log world, it doesn't make that big of a difference, right? So checksum would just mean I'm going to pick some random kind of parity check, right? Add up the x bits in some way and check if Bob also matches that. Okay. All right. So they're very good, like you should think, okay, the way I wrote it here, we don't have to compute the entire encoding first. It's not like I'm writing down the entire encoding and then picking the index I, right? You should think of this I as like a hash function. It specifies a hash function from x to bit, right? So if you know hash functions, you can just use any hash function to make this practical as well. Okay, but the summary is that you get the private thing is like log n plus O of 1. The public thing is a constant because, basically you just have to send something like this. All right, okay. So we have this big gap between randomized and public and deterministic, right? So log n versus n, almost an exponential thing. So summary is we have deterministic of EQ is N, our public, or let's say okay. And while there are no general theorems between, for arbitrary functions, the gap between deterministic and randomized can be big, as big. I mean, equality shows the biggest possible gap in some sense. There's also a very nice theorem from 91, which says that the gap between private and public cannot be too much, which is quite surprising, right? So just imagine that I'm really trying to play poker with someone all the way across the world, and I don't have kind of a shared random seed to shuffle the deck, right? How can I shuffle the deck in some way which is synchronized, which is without communicating a lot of information about it, okay? But there's this very nice theorem due to Newman from 91 to say that whatever gap we are seeing here, log n versus constant, is the worst possible. Okay. You can always assume that there's a shared randomness is completely shared, except for this additive log n. Right? So just kind of initialize some small thing in the beginning, and then you can behave as if they have whatever randomness that you want in the sky that both of them can see. Okay. So this is just to kind of give a sense of the generic relations and the gaps you might have. All right. Okay, now communication complexity by itself seems fairly natural. As I said, it's a very important bottleneck in many systems, so it makes sense to study it directly. But it turns out it also has many, many applications into completely different fields in computer science, in combinatorics, in number theory, in mathematics, and so on. Okay. So for instance, even though there's nothing about time or size in communication complexity, it can imply circuit lower bounds. It is the most important tool for understanding streaming algorithms. So what are streaming algorithms? These are algorithms where basically the data is being thrown at you in a stream, and you don't have the memory to store the entire data. Okay. Just imagine, you basically think of a network router, right? It's seeing packets, kind of sending them through in a stream. It keeps seeing packets. It sees trillions of packets, but its memory is small. It's not going to be able to store the entire stream it has seen, but it might be important for it to keep some statistics about the stream. Like, am I under a denial of service attack? That means that I need to know if the same sort of IP address is pinging me again and again and again. But I cannot store the entire thing because that's way too expensive to do it. Okay. So that's kind of an example, or one of the most important examples of streaming algorithms. Does application surprisingly to optimization algorithms. Like linear programming, semi-definite programming, to data structures, to combinatorics, as we might see later on, and so on. Okay. And one reason all of these things happen is somehow it's more information theoretic. So it's a little easier to understand, and it's more abstract, so it can capture many, many different things. Okay. And it's a very, very versatile tool. All right. So let's take a 5-minute break. And when we come back, we're going to focus on one problem in communication complexity, which is kind of very important, as I said, but also it'll serve as a cue to learn very important technique in communication complexity. All right. So when we come back, we'll talk about this problem called disjointness and a little bit about why it's important and what we know about it. Right? Okay. Let's start in 5 minutes again. And so one of the main things in communication complexity is to kind of build generic sort of tools or methods to understand what's the communication required to solve the problem. Like, often we're not interested in one specific problem. Maybe your application will have some tweak on it or something like that. So we need techniques to understand, like, this will work for all kinds of problems that I want to try. Okay. But nevertheless, historically, one problem has kind of played the role of like a beacon. If I can find a technique which can prove lower bounds or help me understand the communication complexity of this problem, then it's found many, many other applications. Okay. And this is a problem of disjointness, which again is kind of a problem that shows up practically, right? So imagine I have a database of images, or really a database of records, and you have a database of records, and I want to know if there is a common element between the two. Right? Imagine two banks. I keep a list of people who I think are fraud, they're committing fraud here. Some other bank also has a list, and they want to know if there's a person who is in both of them. Okay. It's just database intersection, right? Is there a common element? Is there a duplicate element in both of these databases? Okay? And the way we'll again model it is to say abstract away the structure, because it's typically not important, right? So I have X, and I have Y, and I want to know if X and Y are disjoint. Okay. If there exists an I where both Xi and Yi are 1, meaning that element I is kind of present, is switched on in both X and Y, then disjointness is 0. They're not disjoint. Okay. Otherwise, it's 1. Right. So I have two sets more or less, and I want to check if they intersect or not. Right. And just as before, you can imagine, I mean, this sounds little bit like equality, but it's a kind of relaxed version of equality, right? I just want to check if there's an element which is common to both of them instead of checking if they're exactly equal. Okay. So the deterministic communication complexity of disjointness is once again just n. Okay, there's no savings possible even for this sort of relaxed version of equality. It's still n, but it's technically not relaxed because somehow you might have to output 0 more often, right? They could be almost equal, but still, okay, anyway, never mind. So there's more you're looking to only check if they have a single element in common, or at least a single element in common, right? What can we say about the randomized communication complexity of this problem? The deterministic is n, and it requires a little bit of a proof, but you can do it by kind of a nice, simple combinatorial argument. Okay. The randomized communication complexity, however, is actually quite tricky to understand. and it is very high. So it's basically saying, suppose I have a database, you have a database. If my goal is to check if they have a common element, then there's nothing better that I can do than essentially sending the whole database across. Like there's no clever protocol. I cannot use some hashing, checksum, or whatever. Because hashing, checksum, and so on, they really need equality. There's no way to kind of have only check for overlap. Okay. If there was a good protocol, that would have been very, very useful in practice. But unfortunately, there isn't. Right. And this is one of the most important lower bounds in some sense, because you can use this as a starting point to show many, many lower bounds in communication complexity. Disjointness plays the same role as, like, let's say 3-SAT does in NP completeness problems. You want to show, like, clique is hard or something, then you reduce clique to 3-SAT, right? In the same way, historically, disjointness has played the same role. In some sense, it's like the starting thing that many problems get reduced to, and from that, you can deduce that all these problems are. Okay. And this was first shown by Kalyan, Sundaram, and Steiger in KS 89. Okay. And then it was kind of significantly simplified by Rasparov in 92. Okay. But of course, these are not in 21st century. So why are we talking about this? But there was 2 new proofs, or 1 proof due to Bar Yosef, Chakrabarti, and Yao, and Bar Yosef, Jairam, Kumar, and yes, I forget who the S was. So let me just say BJKS. Okay. So these 2 papers introduced and gave a new proof. Completely new proof of the lower bound for disjointness, and that's what we are going to cover. Okay. So, like, Rasparov's proof for this had many, many applications. He introduced a new technique which has been used repeatedly to prove all kinds of lower bounds. And this new approach also introduces a new technique, which is in some sense, has turned out to be more versatile and has had many, many applications as well. Okay. So what is this technique? This is information complexity. Right. So this is going to be our cue to kind of learn first little bit of information theory, and then how to translate it to protocols. Okay. All right. So with that as the motivation, let me now kind of put communication complexity on the back burner, disjointness on the back burner for a little bit, and just pick up some basics about information theory. Okay. And this is like, stuff that's been known since the 60s from the pioneering work of Shannon. And the main question that this area really asks and answers in a really beautiful way is how to quantify information. Usually when we think of information, we think of bit complexity for representation and so on. Okay. But it turns out that's not the best way to measure information, especially when you're processing things for later on. Right. And the best way is due to Shannon's information theory. All right, so we have to review that a little bit, some basic definitions, and then we'll see. Okay. All right. So what is Shannon's information theory? So think of the following setup. I have some x, which is a random variable, over some discrete domain. Okay, we're only going to look at discrete domain, not continuous information theory. Okay. And information theory answers two questions. One is, in some sense, how random is X? And the next is, if I tell you something about X, how much information do you learn about X? Okay, those are the two questions. And it's kind of complicated by the fact that you have X to be a random variable. For the first one, it only makes sense when X is random. For the second one, it's a complication. Okay, like if I have an image and maybe I tell you, okay, it's mostly in red color, you learn something about it. But if I have distribution of images and I tell you, okay, most of the images are red, do you learn something, or how valuable is that information? We had to kind of develop some way to quantify that. Okay. All right, so maybe let me ask a question first. Let's take an example. The exact mathematical thing is a leap. I mean, it required the genius of Shannon, which was tremendously, I mean, just the definition has been very, very influential, right? After that, you can come up with all kinds of explanations for why that is the right definition after seeing it in action, but I still think it's kind of a rabbit out of the hat to come up with this exact notion. Let me consider a random variable on 2 bits. Okay, so it only takes 2 values, 0, 0 with probability 0.9, 0, 1 with probability 0.1. Okay, and then there's another random variable, which is right. And then finally, maybe something like consider 3 experiments. Okay, I have 3 different experiments where somehow X is showing up, and these are the different distributions that I have. Okay, if I compare, the first one, let me call this 1, this is 2, this is 3. Between 1 and 2, which one do you think has more uncertainty? 2 seems natural, right? Somehow, and if you were to guess, even before looking at X, for the first one, I would always say 0, 0, have 90% chance of guessing the right outcome, right? And here I can guess 0, 0, I only have 50% chance, that's the best. So in some sense, there is more uncertainty in 2. Okay, how about 2 and 3? Which do you think has more uncertainty? Well, maybe still, what do you think? Which seems more uncertain now? Yeah. Still seems like 2, right? Because the first, somehow, if I only had to guess 1, that seems okay. But on the other hand, 3 does have more options there, right? If 0, 0 doesn't happen, here I know it's going to be 0, 1. But there, I don't know what's the next outcome, right? And 1 and 3, again, maybe we can argue that 1 is somehow definitely less uncertain point by point. Okay. So how do I compare these different things, right? Qualitative is one thing, but you want to quantify it in some meaningful way. Okay. There are ways, you could have come up with many, many different definitions, but let me write down the one and only one that actually works. One of the most important notions in many, many different fields is the notion of the entropy of a random variable. Okay. So the entropy of a random variable has a weird looking formula, which is the following. Okay. So you look at all x in this support of the probability of x equals x times log of 1 over the probability. All right. Now, why this specific thing? Kind of why is the log showing up and so on? You can explain it in terms of this is like the expected log odds, whatever the odds language is. But anyway, that's the definition. As I said, it's really a rabbit out of the hat, but it's very, very useful and fundamental definition. Okay. So let's just stare at this for a second, right? You have probabilities. These are always between 0 and 1, right? And then you have log of 1 over the probability. Okay. So at the very least, we know that this is non-negative. Okay. Because, just log of 1 over something less than 1 becomes greater than or equal to 1. So I get. And just sort of as a sanity check, if there is no randomness, meaning, there's only one element and that occurs with probability 1, what would the entropy be? 0, which makes sense, meaning that there is no randomness. Entropy is a measure of how much randomness you have. Okay. So just as an example, if, probability x equals, let's say, 0 equals 1. Okay, it doesn't matter what this A is. If there is a single outcome possible, then the entropy is 0. Okay. And, maybe my domain is like all b-bit strings. And I'm uniformly random over all of them. What's the entropy then? Well, I have the probability to be 1 over 2 to the, maybe let me not use A and B. Let me put n here and n. Okay. So what's the entropy? The entropy is just it's saying somehow the entropy is n, and like you have n bits, so like there's a maximum amount of entropy here. Okay. All right. Any questions so far? And you can compute these things for various random variables. All right. Okay. And one of the important reasons why entropy is useful is we have some nice inequalities for them. And these are highly non-trivial inequalities. Okay, and we will use them. So I'm going to write them down. So properties of entropy. Okay, again, it makes sense for us to have this sort of translate qualitatively desirable properties to quantitative things. Okay, what do I mean? Now, suppose I have two random variables, x and y, or some joint distribution. Okay, if you think of entropy as measuring kind of how much randomness there is in x and kind of measuring how much randomness in y, qualitatively, what should we expect about the total amount of randomness in x and y? Should be more or less than the sum of the individual ones. It should be more than what you're asking for is we would want something like this, right? So this is desirable, like, somehow I'm adding more randomness into it. So this should be true, okay? And this turns out to be true. If you try other notions like measuring bit complexity or something, it might not be true. Okay, so you have to be careful in that, right? So this is true. And how about two together? Have the joint entropy of x and y, how would it compare to the individual entropies? Well, it turns out that it is subadditive. Okay. So the amount of randomness on both of them together is at most the amount of randomness in one plus the amount of randomness in the other. And in fact, something stronger is true. But to do that, I need to define something called the conditional entropy. Okay, so to understand conditional entropy, think of like, here I have 0, 0 and 0, 1, right? So imagine I'm talking about the first bit and the second bit. Now, how much entropy is there in the first bit? What's the distribution of the first bit here? It's 0, right? Because the first bit is always fixed to be 0. So if I tell you the first bit, does it tell me anything about the second bit? Nothing, right? Here, the same thing. If I tell you the first bit, it tells me nothing about the second bit. But here, if I tell you the first bit, it can tell me something about the second bit, right? If I tell you the first bit is a 0, then I know that the second bit, 0 or 1, is kind of distorted, right? On the other hand, if I tell you the first bit is a 1, the distribution on the second bit changes to being 50-50 instead of being 90-10, right? So in one case, it's giving me kind of reducing the amount of uncertainty left in the second bit, right? And there is a way to quantify this, and this is called conditional entropy. Okay, so what does this notation mean? I'm going to sample from whatever I'm conditioning on. Now, once I condition on this particular value, I have a new random variable on x. And I'll check what is the entropy there and what's the expected entropy. That's the conditional entropy. Okay, maybe on some samples, it completely destroys the entropy in x. On some samples, maybe it keeps most of the entropy in x. So you're just looking at the expected entropy left after seeing y, right? And how should you expect conditional entropy to relate to the individual entropy? Like this joint variable x and y, if I tell you y, how should it affect the amount of uncertainty in x? Less than or equal to, right? Somehow I'm giving you more information. Maybe it's useless, but it shouldn't like increase my uncertainty, right? It's not really true about all knowledges. Sometimes more information can make you more uncertain, but at least in math, it doesn't happen because you can kind of ignore the information about y and you should have the same thing. Okay, this is also true. I mean, these things require proofs because you have logarithms and so on. You have to work towards proving it. We're not going to prove it. Some of these things involve Jensen's inequality, so you're not going to prove this. In particular, this one is tricky. And this one's also tricky. Okay. And lastly, in fact, we have something stronger, which is this. And this is called the chain rule. Okay. This is saying the amount of uncertainty in x and y is uncertainty in y plus whatever is left in x after I tell you y. Okay. So all of these are fairly intuitive, but if you actually work through these as your axioms, you'll end up with that being the only definition of h of x which allows these things to be true. With the weird log and so on, that's the only definition which satisfies these properties. Okay. This chain rule in particular is very, very important. Any questions about this? I mean, there are whole textbooks and courses. I'm sure there's a course in, for example, the E department, which is only about information theory, right? But we're not going to talk about that. We're only going to pick up kind of the basic definitions and one or two important things that we need to use it for our application to information complexity. Okay. All right. So we're almost done. I just need one more important definition. And this is the notion of mutual information. Okay. So once again, I have two random variables. You know, they need not be independent. They're over some joint distribution. What I want to quantify how independent or how useful one is in telling me about some properties of the other. Okay. If we both toss coins independently, then knowing the outcome of my coin toss should tell you nothing about your coin toss. Okay. But let's say, I'm rolling a giant die and I'm on this side of the dice and you're on that side. If I see my face and you're seeing that face, then if I tell you my outcome, you know what your outcome is. Right? Okay. You can also imagine doing the same thing where we roll two giant dice, right? And if I tell you the sum that I see from this side, it won't fix your outcome, but kind of changes the distribution a lot. Tells you something non-trivial about what you would see as the sum. Okay. And mutual information is like a very nice and pretty much the only way to quantify that in a meaningful way. Okay, so what is this? This is, there are different definitions, but okay, let me write it this way first. So what is this saying? This is the amount of entropy left in X after I tell you Y. So if I tell you Y, how much uncertainty is actually still left in X? Okay. And it requires a little bit of work, but you can actually show that this is true. Okay. It's the same as how much entropy is left in Y after I tell you X. And finally, I mean, you can take one of these as a definition, the others are proved, like, things that you have to prove, right? So like we had this inequality here, right? It's a gap in this inequality. That's the mutual information. Okay. So if X and Y are completely independent, then you should expect the mutual information to be 0, right? Because knowing Y tells me nothing about X, we want it to be, it should be 0. And kind of holds, if X and Y are independent, H of X given Y will actually be 0. Will it just be X, so it kind of vanishes, okay? If, maybe X is completely determined by Y, then knowing Y, the entropy left is 0, so it'll become full, okay? All right. So, just as an example, let's say X is in 0, 1 through the N, but Y is 1 minus X, right? Then okay, because I have H of X given Y, but once I know Y, there is no uncertainty left in X, right? So this is just H of X because this is equal to 0. Okay. All right. Then where all of the properties let me state a couple of things in just a slightly more general form, right? So chain rule for entropy. The chain rule for entropy, we kind of saw the 2-variable version, right? So this is the 2-variable version, but I can iterate it, right? Meaning, so suppose I have x1, x2, all the way up to xn, right? I can write this as h of x1 plus h of x2 up to xn given x1, right? But I can then also write it further as okay, and so on and so forth. The exact thing that you get is let me write it in the summation notation. The amount of entropy left in the jth variable conditioned on the prefix so far. So imagine you have x1 through xn. I tell you something about, I tell you x1, and then I ask you to guess x2, and then I tell you x2, and then you ask you to get s3, and so on. Okay. This is a chain rule for entropy. And there's a similar chain rule almost from the definition, because mutual information is kind of has the same equalities here, right? So I can use chain rule for the first one and even the condition one and get the following. Okay, so if I have I of x1 through xn, comma z is equal to Okay. So just as we have the chain rule there, you'll also get a chain rule for mutual information, but you just have to condition on the prefixes. Okay. How do you define conditional mutual information? It's just as we define conditional entropy. Okay. So you can talk about, maybe let me write that one thing down. I of x comma z given y is okay. So I already know y, how much information is left in x given y, and then how much additional information does z give me about x. Okay. So more or less all of these are what you expect them to be true qualitatively. They turn out to be true, but as I said, they are non-trivial. It is non-trivial that they are true. Okay. If you try other versions, maybe don't put log, put some other function, it's not going to be true. Okay. All right, so let me stop with this today. And when we come back, we'll see some, just this chain rule and subadditivity is by themselves are already very powerful. The power is very much hidden in the definition and the non-negativity of mutual information. Okay. Can prove some very important things in combinatorics just using that. But we are going to do something even more sophisticated. We're going to use it to prove communication lower bounds, right? Okay, so that's what we'll do. Not next Monday, but a week from now, because next Monday is a holiday.